Okay, now we want to talk about what happens if we do include a resistor here. Well, a resistor gives us a voltage drop across the resistor that's just directly proportional to and in phase with the current. Okay, so that the voltage across the resistor, don't really have room to write it up here. I'll go ahead and write it this way: VR equals R times I max cosine of omega t. Okay, and here's our VL. Have trouble reading now. Just barely have room to squeeze that in. Okay, and hopefully you can read that. It's kind of up there in a little bit of glare, but it should be visible. Okay. And that's simply because, well, that's Ohm's law. Okay, you just multiply the current by the resistance, and this is the current, this is the resistance, and you get the voltage across the resistor. The current is regarded as an instantaneous response to the voltage, so there's no phase lag, no opposing voltage as a result of a resistor. Okay, so what does that do in our phase diagram? Well, that puts the resistor voltage in there. So now all this stuff outlined in red or orange or whatever this color is, pink, here, here, and down here has been added. Okay, none of this stuff is relevant to anything that we did previously with the LC circuit. Okay, so the LRC circuit is governed by this phasor, and this gives us a relatively simple analysis. Okay, the resultant voltage then is here, as opposed to the resultant voltage that either has to be this way, or in the case of resonance, 0. Okay, so the source voltage now, and I got VR down here, so that was bad labeling. I used R thinking in terms, I don't remember exactly what I was thinking at the time, but I believe I was thinking in terms of resultant, but who knows. Okay, so I'm going to write out the word resultant. Hopefully you can read at least some of those letters. And before this thing collapses, let's straighten it out. Okay, here's the resultant of your inductor voltage, your capacitor voltage, and now your resistor voltage. Now, if you got more resistance, your resistor voltage is going to be bigger. Less resistance, less. If you got a huge voltage resistance, then it's going to kind of overwhelm the voltages of your inductor and your capacitor, and the circuit will behave very much like it would if the inductor and capacitor weren't even there. Okay. Now, according to this diagram, the inductor and capacitor voltages add up to, well, about this. So I'm going to let this little arrow be your VL plus VC vector. Okay, and of course that vector rotates along with everything else according to the way the phasor works. Then you have, perpendicular to that, your VR vector. Okay, so if you got your VR here and your VL plus VC here, then what's your resultant of the three? This is the resultant of these two. You add that to this one, and you get this vector. Just doing a parallelogram method. We have projection lines here and here. So now we have this phase angle here. Okay? Now this phase angle is actually in the negative direction, and I'm going to say negative phi. This is actually phi. I got a little bit fuzzy with the positive and negative signs, but this is going to work out. It worked out originally, except I have a negative sign there, and we're going to take care of that in a minute. Okay? So if this is negative phi, then the tangent of this angle, okay, just according to, let's say, this triangle here, is the opposite side, which is VL plus VC divided by the VR, okay? Now, the VL plus VC is this. That's basically your V max. It's your 1 over omega C minus omega L times I max. That gives you your V max. Your V max for the resistance is just R times I max. So if you take the opposite side here, it's going to be 1 over omega C minus omega L, magnitude of that, multiplied by I max. And the length of the adjacent side is just, I'm sorry, this is the adjacent side here. Well, that's, okay, never mind. Okay, this is the side opposite this angle. Okay, this side is adjacent to something, but not to this angle. So again, this side is your VL plus VC. This side here is the same as this, which is has this magnitude. The adjacent side is your VR, which has just magnitude of R times I max. When you divide this times I max by this times I max, you get this divided by this. Okay? Now, I didn't put absolute value signs around anything because, let's see, now this angle, the magnitude of the angle that we get here is negative phi. Phi is negative in this case. And that tells us that negative phi is the inverse tangent of this over this. Okay? Meaning that phi is the inverse tangent of this. The tangent being an odd function. The inverse tangent is also an odd function, so when we change the sign of what's inside, that changes the sign of the inverse tangent. So here's the phase angle. Now, that's pretty astounding. Just from this picture, we get this phase angle, which fits right into the solutions to the differential equations. Now, you don't need the solutions to the differential equations, but you should have them. You should understand how all that works together, because it'll give you a big head start on subsequent courses. So right there is our phase angle for an LRC circuit. And it just comes out of this picture in what should be a very simple and obvious way. Now, looking a little further, and let me pause to get my thoughts together. Let me clean up one little detail here. I labeled this as negative phi. Well, phi is in this direction, so phi is negative. If I do this, then the angle is just the magnitude of the angle, and the magnitude of that angle is negative phi. And the tangent of that positive angle that I've now drawn here, negative phi, of course, the magnitude of that positive angle, or the tangent of that positive angle, is this side over this side. That led us to the expression that we have up here. And if I draw the angle like this and label it as negative phi, then we know that phi is in this direction, and everything works out. So you can think that through. I'll be glad to answer questions on that. Okay, main thing I needed to think about was how this is garbled. Okay, all this stuff in here now was added. Now, this plus R I max cosine of omega t, this is your voltage across the resistor. I've added that in to the voltage across the capacitor and the inductor. This times all this is your capacitor. This times all this is your inductor. Now, we have all this is a multiple of the sine of omega t. This is a multiple of the cosine of omega t. So the magnitude of this thing is going to be the square of this plus the square of this. The sine and cosine being opposite, being at right angles to one another. So we just have two legs of a triangle basically adding up to the large leg, so that the maximum voltage in this case will be what we get. Now, this is a little hard to read. I'm going to rewrite it in a minute. But it's just the sum of this squared plus this squared. There's your R squared. That square is a little hard to read. And there's your I max. Now, I did smudge something in there that's supposed to be a max. Okay? So we have V max equals this. Now, I'm going to rewrite that just to make it easy to see. Okay, I don't know how much clearer that is, but that should show up pretty well on your screen. We just have 1 over omega c minus omega L quantity squared, this is the square of this thing, times R squared, and then I didn't write the I max here. So that's times I max, and kind of wall that off. It's intruding in my parentheses here, but hopefully that doesn't confuse the expressions. Okay. Now, what's that mean? That means that V max over I max is this. So that means that this is the total impedance of the circle, of the circuit. We got circles, we got circuits, and it's getting kind of late in the afternoon. I need to eat supper. Okay, so we have this. So we have, we'll put it this way. V max equals Z I max with Z equal to the square root of this thing again, 1 over omega C minus omega L squared plus R squared. And we see that Z is, again, like a resistance. But now it's the sort of an equivalent resistance for an RLC circuit. And it's not really a resistance, but it does help us relate the maximum voltage and the maximum current. That, along with the phase angle, allows us to determine the behavior of the circuit.